to Dr. Mehmet Akşit here at Emeritus. His research made foundational contribution to software engineering, programming languages, and software architecture. It's a pleasure having him visiting us. He served as full professor and chair of the software engineering department at the University of Twente. He has held visiting professorship and research appointment at IBM Research in US, New Jersey Institute of Technology, the University of Tokyo in Japan, and University of Malaya. Between 2020 and 2022, Mehmet was having an international fellowship for outstanding research programs. He served as professor of digital disaster management system at top University of Economics and Technology in Ankara. And I let him continue introducing himself much more in depth and with the talk. We are trying to do this in 30 minutes, so it's getting time for Q&A. Thank you.
Thank you very much. So hello, sorry for the delay. Apparently there are two buildings with the same name in different locations, so they dropped me at a different location. The talk is so as Ali Askari asked me to emphasize the problems that Turkey has experienced with the last large earthquake in February 2023. So I put it as the focus here. Anyhow, I will be talking about disaster management systems, and then I'm by myself, as you heard, a computer scientist, but the last years I have been working on disaster management systems, and I think there are a lot of things that can be done there. And I was a professor at the University of Twente for more than 20 years. I was the chair, and then I had to retire. That's the rule in Netherlands. When you get older, you retire. And then I went to Turkey by invitation, so then I could set up my group, and I cooperated with the disaster management agency there. It's a very large agency in Turkey. And then this work is based on actually my experiences there. And at the same time, I had PhD students in Turkey. So we work on, and also in the Netherlands, we work on disaster management systems. So basically this paper focuses on this talk. The first part at least focuses on this paper. And it is about digital twins for disaster management, mitigating structural obstacles in the response pipeline. This paper I can provide you, but of course there is now a typesetted version. It will be provided by Elsevier. And here we show that actually inherently disaster management systems, they have structural obstacles. And so what is a disaster management system? Typically, every disaster management system in the world has this linear structure of pipeline architecture where the emergency conditions are reported and they are checked if they are really fake or real, and they are registered, and then planning and controlling actions are initiated, and then the tracking and control of response operations are carried out. So we say that so I call them handlers in this sequential pipeline, so the throughput of handling an incident is related to the capacity of reporting channels, the number and efficiency of operators. Most of the time, disaster management systems are operated in general manually, although they use, of course, sophisticated devices. most disaster management systems have large screens. Operators see what is going on there, and then they actually delegate task forces and resources to the area where disasters have been experienced. And what we see here is that every phase has limitations, and actually the throughput is determined by the weakest phase. And even if you increase the number of capacity, beyond certain limit, you cannot really increase that much because of the also manual processing and sequential pipeline. For example, in Turkey, when the big earthquake has happened, 1 million reports have received in a very short time. And how many people you want to employ to deal with 1 million reports? So it's impossible actually, and they have to also coordinate. The operators have to coordinate as well. It's not only individual independent operation. So basically what happens is that I will show here in detail that after some point, they cannot process, so they cannot register, queues appear, but the political pressure actually, and also, of course, everybody wants to move towards the disaster area, so they have to send their task forces without knowing actually what's happening. So this is quite common actually in most disaster management systems. So we have been working on this, and of course we have studied data and all kind of reportings about the incidents. But let me talk about digital twin architecture as I observe it or I see it. It's a typical definition of digital twin is a virtual representation of physical objects, a software and hardware system or a process referred to its counterpart, and very important property is that it's synchronized with real-time data. And what do you do with that? Simulation, analysis, monitoring, and control. It's the common application of digital twins. And actually, I have been, of course, in the computer science field for a long time. We used to have conferences, and many people were working on so-called reflective computation. And actually, reflective computation is very similar. So you have base modeling and code, and reflective modeling is a representation of the code. So if you change the model, then the code changes, and if you change the code, then reflective model changes as well. So digital twin is very similar, but of course, there were also languages, and of course, many languages nowadays have some kind of reflection, although full reflection is quite complicated. But of course, digital twin brings it, this topic was studied in the language domain, but of course, digital domain is more general, but the ideas are quite similar. Another related work is software control systems. So here mainly I show hardware, but it could be also software controlling software. What you have is a control system, a system being controlled, and you want to sense actually the parameters that you are interested in. And with feedback, you have actually model of the system that you want to control. So this we could call digital twin model. Of course, digital twin requires mechanisms. All other components are actually providing synchronization and so forth. So actually, digital twin is a software control idea, which of course it has been there for many, many years. Of course, traditional control systems were more mechanical control, so the models are more differential, based on differential algebraic equations and continuous systems. But of course, we know that last 30 years, many software systems were also based on software-based software control. So I think digital twin is about the same idea, but it's a more popular name. So I studied in Eindhoven in Netherlands of control theory, one of my master theses. So actually, of course, what we were studying, it mostly was in a different context. So digital twin approach is a control system approach. Basically, you can do it for monitoring. If you only have this, you have monitors. So you compare the model with the reference model, and if you have errors, you take controlling actions in control loop. If you don't have control loop, then you are monitoring basically. So basically in the literature, you see descriptive models, predictive models, and prescriptive models. So the order is most of the time, first you want to understand what is happening, and then you may predict if necessary. And then if you want to have improvements, you can have prescriptive approach or modeling approach. So this is actually a representation of a very large, very big disaster management system in Turkey. But in many places, it's about the same. So you have reporting channels, incidents, you register, plan, and control. And the operators give orders to the task forces. So we can have actually three kinds of digital twin models on the top. Descriptive analyzes actually the events and then sees if they're try to detect if there are some anomalies. And once anomalies are detected, you may also analyze the situation based on some scenarios. Mostly you would like to know extreme conditions. And then based on the observations and knowledge, you can also provide suggestions to actually increase the efficiency, effectiveness of the processes. So let's see what we have done from this perspective, application of the digital twin as a descriptive mode. So how do you evaluate, how do you define descriptive models? One way of doing that, and actually most, I think, logical way, is to define KPIs, key performance indicators, and try to analyze the system based on KPIs. I must say, I was very surprised when I started working, doing research on this field. I was very surprised that no KPIs were defined for disaster management systems. So we have a publication, a different publication on key performance indicators of disaster management systems. And at one event, I was talking to a Canadian responsible person, not Professor Alaskari, but a different person. I said to him, why never define KPIs? How do you think that you want to improve? For example, there is no data about how successful the firefighters are or rescue teams are. No formula, no one single reference. So we divided about 22 KPIs, and here we have used also some of them. And the guy said, the Canadian guy said, well, if we do that, then we can be accountable. So people can actually say to us, you promise, let's say 7 out of 10 is a quality value, but now you function as 5, so you should pay us some money or some compensation. This could be the reason, but I was very surprised. Therefore, no data is available about performance of disaster management systems and also task forces. So what we did is define the KPIs, so I will go quickly, and actually use these to describe actually how a disaster management center is operating. So I'm not going, because of time limitation, I'm not going into detail, but you can imagine that we have, for example, pipeline recording efficiency, pipeline processing efficiency, incident awareness time, intervention start time, and so forth, pre-recorded response. So these are all measurements we made. How do we do that? we collect information from past data based on fire or forest fire and earthquake. And then we measured actually the properties. So these are based on real data. But later on, I will mention that actually, unfortunately, because of limitations of the pipeline, data is also not recorded well. So we also look at various disaster management centers. It's about only 10% of data are reliable in these centers because of the chaotic situation. Also, data is not recorded. And the data you want to know, you want to record, these are not based on not known concepts like KPIs, therefore they are not also kept. All right, so we collected them. So here we have incident type, only two things we look at it: interval time, occurred incidents, recorded incidents, respondent records. You see that recorded incidents are much more than the response. So they are recorded, but there's no response. It could be possible that multiple reports have been received for the same incident. At the same time, which we observe is that after some rush, let's say, reports, many reports arrive and they cannot be handled. So approximately now about 60 people can handle 1,000 reportings. So if you have 1 million, you are really in trouble. Okay, so I don't know if you want to keep short, you should just trust me that we see that there are anomalies here. For example, the intervention and start, and there is also a gap between them. Okay, summarizing. So I promise to be short in this presentation. Summarizing, we have analyzed, and you can see in this paper I can provide you, that there are some indications that, especially in the forest fires, we have observed. But although data is not really reliable, we also have another publication about reliability of the recorded disaster data. So we have seen that actually there are some indications of problems here. So what we did, secondly, is to build a simulator of the disaster management system, because we want to test also extreme conditions. With the same disaster management operating center, we want to test it with extreme conditions. For example, Istanbul earthquake is expected, and then nobody wants to think about it, but it's a reality. And what will happen to the city, and actually how efficient and effective is the disaster management system to handle such kind of requests. Of course, we know that the big disaster in February 2023, many things could not be registered and could not be followed. Okay, so how did we do that? This is the simulation architecture. So we have a city configuration. We didn't do it on a real city, but we generate city. And then we have emergency generator. These are really tunable. You can adjust the probabilities and everything. And the idea here is not to define a realistic simulator to test how vulnerable an existing city is. No, we just want to generate your emergencies with reasonable accuracy in the sense of probabilistic behavior, but we want to test actually the existing disaster management system. So the idea here is to test the system, but not to create a realistic simulation system, because this is out of our scope. So then we have a model of the disaster management system on the two blocks there. So we could do these simulations in various ways. We prefer to do it in discrete event simulation. We could use also AI techniques, but we wanted to really have what-if analysis. If you do what-if analysis and the analysis of the behavior of system, and to understand actually how the system behaves, we found out that discrete event simulation should be actually more meaningful. So the city configuration, we are explaining how we do that in the paper. And emergency generation, basically we create emergency of different degrees. So how do we do that? The buildings have some resilience factor determined actually by the construction engineers and earthquake engineers. And then we have the intensity of the earthquake. So we calculate whether it's damage or not. Of course, we can increase the intensity. These are all based on probabilistic stochastic variables. So we have emergency generator applied to cities, and then we get some results. Okay? And then the registration process is actually based on the existing configuration of disaster management center, about 60 operators. Registration and checking the validity of the report takes about 8 minutes in average. And the planning, the actions takes about 12 minutes. And this is actually the setting based on the values. You can, of course, this is the city generated, divided into different regions based on, for example, ground mechanics of the buildings. And then we can just adjust the configuration as we want. I'm just talking about there how we adjust. And the earthquake is centered at the location and starts at 3 minutes, and the arrival increases. So what we have is generate and reduce the rate of reporting. Okay, so this is actually the simulated arrival rate example, the cumulative number of emergencies and arrival time. And this is actually the delay in the pipeline. So the delay in the pipeline, we can see that based on realistic simulation figures, the request cannot be registered. So this is also waiting time, queue time and waiting time. Here, but we see that there is a clear, of course, when you look at these figures, they match also the queuing theory. You know, if you study computer science, you study, I think not nowadays, but in my time, most students hated queuing theory because most students got bad remarks. So this conforms actually all the theory, queuing network theory. Okay, so what do we do? What do we do is we analyze the bottlenecks, and actually we try to understand, or we try to detect where actually the timing and the delays are created, and if we can do something about it. Actually, I have been working on these digitalization techniques for quite some time, and we have all kinds of proposals for that. And what we call, for example, ADOPS principle is we try to actually minimize the waiting time and processing time by developing digital techniques along the pipeline. We cannot avoid the pipeline, but we can make it much faster. So these are the objectives: diagnose root causes identified by descriptive and predictive models, identify solution domains, compare alternatives, and select based on cost-benefit trade-off, estimate impacts and validate via simulation, interpret results in terms of maturity, cost-benefit ethics, position findings within broader technology trend. So you should also look, of course, I may be seeing these sensors or these technologies and how does it develop further. So we did this actually for quite some time. I must say that when I was asked to be to bring my research to disaster management agency in Ankara, about at least 10,000 people are working, but with volunteers about 100,000. It's the largest budget, and the last earthquake cost 150 billion dollars, American dollars. This earthquake cost 150 billion American dollars. So it's like it's a very huge, of course, amount of money. And so what I did there was I also made interviews. It's a software engineering tradition to talk to the stakeholders and the customers. So I have made also interviews to the rescue teams and see what they are actually missing and wanting to have. And actually all these studies also confirms these experiences. So both practical experiences. So we did basically a requirement analysis process like we learn in software engineering from multiple stakeholders' perspective. Okay, so the root causes pipeline architecture creates structural constraints, causing sequential bottlenecks. Manual processing further reduces throughput and lead to loss of control because when a big disaster occurs like earthquake, you have about 15 minutes. You have to send all your resources, otherwise too late. So there's a pressure. So when you say, for example, Turkey is very rich of drones. They have many drones in Turkey, very sophisticated ones. Also disaster management agency, but it takes 2 hours before it goes up, circulate around, and the weather must be good. And when the big earthquake has happened, the weather was terrible. You may have, of course, dedicated radars for that, but still, it's too late. So my constraint was with students, I always say we have about not more than 5 minutes to do everything. And we were able to do so. I will show you some examples. So what we did was the manual processing of registration operations, manual processing of planning operations. 2 things were, for example, bottlenecks here. You can use multi-sensor smart fusion technologies. We have a paper on that. We try to very simple sensors. Sometimes you get very good results. We have also experimented with about 40, 45 sensors and information sources. I will show you, we have a paper for that. We actually define a sensor fusion design environment we designed, which optimizes actually the number of sensors with the highest efficiency of detecting. So what we need is precision, of course, cost and time. These are the critical factors of this detecting. So let me show you the cheapest way of detecting whether building. So 2 things. What has happened after a disaster and where are the living people, And you want to do it the shortest possible time and shortest possible, least possible cost, because otherwise you cannot do. So the cheapest I found is actually a collapse detector you put on the wall, and when a wall collapses, it gives you a signal. It's about 75 cents or $1 maximum. And the second one is dust detector. They don't use for earthquakes, but they use it for factories, some factories where you create dust. It's also 50 cents. So if you, in a floor, you put it in a building for, of course, you have to be smart, somehow expert. 4 dust detectors, so 4 collapse detector, 1 dust detector per floor. Only base floor is about 35% of accuracy, but if you put it every floor, then it's almost 99%. So you exactly know which floor collapse. Then you need a computer to collect information. I call it black box, so it should be safe. And then we use a narrowband transmitter. It's about $10, which transmits easily 70 kilometers. So you have it in the few $100 a building, you know, whether it's collapsed or not. I think it's the cheapest. Detecting living creatures is a little bit more costly, but you need more processing, but you can do it up to 85%. So I computed here I exaggerated. I put too much. You know, I put for the most expensive building in New York or so prices, so they are cheaper than this. But I said I'm submitting this for review, and the reviewer comes from a rich part of the world, and he will price is too low, so I better put them high. Anyhow, doesn't matter. This is just examples. So you actually get it much faster. So if you put more money in, so it can even reduce to milli. So for us, it's 100 milliseconds or so, you can detect these things. And if you put enough, you can almost bring them to zero, this process. But if you cannot put everywhere, then of course ethical questions start. So where do you put, which people you privilege? So there are also ethical issues here. But here the diagram show that, simulation show that actually we can really reduce the queues and improve the speed. Okay, of course, when you do these kind of technologies, I hope that I'm now also in the presidential referent, how do you say it, expert group on these kind of things. We are negotiating, and hopefully governments may actually oblige during construction to put these devices, integrate them in the houses, especially for earthquakes. But of course, they can have different kinds of composition of sensors for flooding and other things. So I think it's doable, and the clue is, of course, communication technology, but sensor fusion. I think you can never rely on one sensor. The question is where to put sensors, and so we developed algorithms to compute actually where to put sensors and which sensor, how many times. You can optimize this. So I think I was looking this one, not this one. Okay, so I'm not going into detail of this. Okay, so all right. So another paper which is also accepted published, I won't go into detail of this. Actually, we analyzed the errors detected in disaster management sensors. The errors happen because when you cannot handle this high flow of information, mostly they are registered afterwards, sometimes several months after, because government employees are also responsible for accounting what they have used as resources. So they have to fill the forms. I then distributed 2,000 blankets, for example. They have to say it where they spend it, and they just put it. They just put it in the data afterwards. So the errors are, this is a feature diagram, if you are familiar. It's not an inheritance, but it's a feature diagram, which is based on basically propositional logic. So there are alternatives and options and so on. So the next one is performance-related errors. That means there's no data available, or the data collected about the performance of the system is not correct. So metadata. And this doesn't exist basically. Performance-related data nobody collects because nobody thinks of such a thing exists. So machine learning doesn't work if the concept is not known. You can only do something if the concept is known, but here the concepts are not known. So this part really doesn't exist in general, but we started collecting this part. This is most of the time rescue-related errors. So what are these missing incident data, incorrect incident data, imperfect incident data? Because mostly human beings are entering, they also can't just make subjective decisions and so forth. So when we had the analysis of this, we have found out that actually only 10% or less than 10% of data are reliable. So you cannot, everybody says we should have disaster management data, but they are not reliable because they cannot be processed as desired. So people just fill in. to satisfy the politicians, basically, most of the time. The government wants to get the statistical numbers, they just put as government wants. Yes. So this is because of basically not being able to process on time and because of the queues and so forth. So it's quite serious, but there is no publications about these kind of things. Universities assume that the data they can have is really of high quality, but in fact, our experience that it's not. So what did we do there is we use digital twins. These are all digital twins. So what we do is this is disaster management system, and the top we have digital twins, and digital twins are for corrective actions. So what does it mean? This means if we detect some anomalies, well, one of the most common anomalies are the time, the causality of operations and time. Sometimes incidents are said or written completed before the incident occurs. Actually, this is quite often. Many of these kind of mistakes, the paper has all in detail, and actually we analyze them with all statistical analysis and machine learning techniques. We classify the errors. I'm not going to go. But what is maybe interesting is that you can use also digital twins as a corrective corrective control mechanism. So basically, in control and recovery, you can do it, you can prevent errors, or you can do backward recovery or forward recovery. Backward recovery is difficult because of the stream of data flowing. Basically, all these are doing forward recovery. So get the data, analyze it, and correct it. Okay. So what are these transactional digital twin? What we have seen that actually, if you now study computer science, you know that data should not be accessed simultaneously. Write, read, write conflicts. If you do write, rewrite operations on the same data becomes inconsistent. And here we see a lot of these things. So what we do is that we pack them. We can detect actually when the code is executed, read, write. We put them in a transactional semantics. That means we do, for example, depending on either optimistic or locking-based modulus control. Process, we check if the process follows the defined order, because the operators can really jump in the process, use different tools. They can do, let's say, intervention, but at the same time go and play with the data about the reporting data. So they can just go, and therefore actually the causality problems occur. So these digital twins are used for forward recovery most of the time. Okay, we have prototypes of that. So what we see is that actually you can use digital twins for different kinds of purposes. Finally, I want to show some more publications. So this publication, for example, is about detection using sensor fusion. So this is about sensor fusion algorithms to increase the reliability of detection. And it is, one information source, let's say, of course, at the most you can get 100% probability or full, let's say, probability of 1. But if you get, let's say, like this, probability 1 is this, but when you add sensors, they increase, asymptotically goes to 1, of course, so you can increase the detection probability. Here we show, here we describe KPIs. Without KPIs, how do you think of improving the system? This is the first publication. This is the first publication on this. And here we define the demand generation. We analyze the disaster, and we say we need so many, let's say, firefighter teams, ambulances, police, or distribution of food. So if we estimate by analyzing the disaster event, estimate what kind of resources are needed. This is so crucial. If you detect, of course, they are dependent. So if this works well, this works well as well. So if you detect exactly what has happened. Our experiments show that within, let's say, less than 1 second, we can get almost, and if you, of course, install everything as desired, we can get almost 95% detection of the incidents in, let's say, less than 1 second. And then we can compute the number of required resources. And the thing is that, of course, how do you compete? You cannot apply machine learning because no data is available. We work with ontologies, fuzzy ontologies, which are machine learning tunable. So we define in such a way that when data is available, you can tune the ontologies actually. We have publication also just accepted. And then we have also event-based digital twins. So if we continue, finally. We recently we built everything as agentic, based on agents, smart agents. So we have actually cooperative demand generation agency systems of systems. These are, so this generates demands based on cooperative agents. So one agent gets, let's say, a view on it, other agent gets at the same time. So you need to cooperative agents. And this one actually does multi-objective routing of task forces. So all these, as you see, actually improve the efficiency of the pipeline. So my final slide is actually, we have this pipeline process, and we can really improve the process, and actually computer can handle millions of incidents. So it is doable. So we have 3 kinds of digital twins. Evaluative is used for analysis. As I showed, descriptive, predictive, and prescriptive ones make analysis. And then corrective actually corrects the errors, either prevent them or forward backup or recovery. Mostly it's forward recovery. We know that forward recovery is not easy, but since we have a good semantics of what's happening, so we can apply forward recovery. So feedback loop corrects actually on the fly. And then we have calculative, where we calculate the sensor vision, the automatic demand generation, optimal allocation of resources. And we also manage, for example, resource demand conflicts when there are not enough resources for the demands. We have all kinds of technologies that can handle it. In current disaster management system, if the number of incidents reach the value of number of operators, queues occur. It goes like that. In our case, computer detects it just goes flat. And if the number of resource demands are more than the available ones, also it gets even worse. But in our case, because we can do very fine-grained optimization based on priorities and all kind of multi-objective reasoning, for us, you don't waste that much resource. So this is actually, we are focusing on end-to-end automating. So currently, if you see it as a very big, sophisticated system, but unfortunately, it's manual decision-making, like in many places in the world. I have seen disaster management centers in many places in the world. Manual processing is the default, and these publications are novel. That means they don't exist. So we can really save a lot of lives. And after my retirement, this was my motivation. Many people are trying to kill people, but we try to save lives, and I'm proud of it. That was my talk. Any questions?
I have a bunch of questions myself, but let's see if people online or I saw that in messages. We have questions online?
There's one.
Oh, sure.
Yes.
Thank you very much for your speech. Outstanding publication.
My ears are not.
Oh, no, I will speak loud. I have a question about the sensors you installed in the buildings, because in that situation, for emergency situation, especially in earthquakes, I think it's very important to have the structural damage is very important because the whole building will collapse. But when you put the sensors around on the buildings and also using the sensors of the dust, so maybe there should be some cracks or some damage to the walls that may send you too many or too much information and data to your system or the control base, which is not that emergency, comparing to other with structural damage. That one building is collapsed, and that would be more important to have the too many walls that have cracks on them or many dusts that maybe happens because of many other things, like gas explosion or any other things. So gas is important, the gas explosion, but maybe other things that may cause in that situation.
Exactly. So actually, you are very right. So there are two groups. Traditionally, earthquake engineers want to actually know if building is should be kept or livable or sustainable. So they try to assess the damage more precisely. So we have earthquake engineers doing that, and so they have to do more precise work. Also consider the construction. In our case, I have some good. I mean, I have connection with colleagues in this respect. So we appeared also. We were also at the same workshop discussing this. They need much more dedicated, detailed model, because they want to say if this building has to be kept or not, for example, but we don't do that. So ours is just starting intervention, see what kind of intervention. So there are some good publications on that. The thing is that it may take too long to have detailed analysis. So there are somehow, I know some publications, some people working on that, try to do it in 20 minutes or half an hour. In our case, it should be milliseconds. So that's the difference, yeah. But exactly, you are right. So the question is, can we combine these two techniques together? So they have of course much detailed knowledge. They need much detailed knowledge about the construction and the quality of concrete and so forth. Yes, you are right. So ours is somehow we want to know what kind of risk and where are the living people and so forth.
Maybe at the assessment after the post-disaster assessment.
We wanted in everything should be set in at most 15 minutes, because you have to send. Everything should be sent. So you cannot do it. Yes.
So when you're talking about requirements engineering, I get so excited because I'm also a requirements engineer. You know, I field of research and my students are all doing that. Yes. So, and we know that there is not much of that kind of work, you know, in disaster response and management and so you did the interviews. What happened? Like, what was the outcome of those interviews that you explained?
Yes, we did the interview. I prepared questionnaire and of course I read all kind of literature and everything.
Did you publish that?
So
did you publish the results?
No.
No. Okay.
I had the interviews and everything on my computer because I discussed. So what happened is as follows. I asked AFAD, Disaster Management Agency, to give me collect people for me from the field. So with these different disaster experiences. So they came and worked before the big earthquake. So then I classified from different perspectives, from disaster management perspective, system design perspective, and software perspectives, so different perspectives. And it took about 3 months.
Wow, how many people?
So what happened is actually about 2 phases. We did about, let's say, 30, 40 people from the field, and then I put the results on the experts. So they are experts on different disaster types. We discussed with them 3 months.
Oh, wow.
The first, I mean, not every day, day and night, but let's say twice a week or so. They have to work as well. At that time, I was working for university in Ankara. So the most difficult question, the discussion was, actually I have all this here. Maybe if you have time after I can show you. Then the most difficult question was what to automate and what should be manual. This takes about 3 hours, only this point. So I said in my report, if needed, everything should be, manual, not everything fully automatic. And then that was a hard debate. So then we prioritized. And the prioritize was based on, because they all wanted everything, but they wanted. So prioritization based on the criteria that if you can add some feature later, then we should defer it. Some features cannot be added later. So I have this study, and then we look at what kind of skills are needed to address this. So I have a report on, we need about 32 different kinds of computer science experts, plus of course, earthquake engineers and so forth. I have
Very
this
interesting. I mean, my students are looking at me because we have done something similar. I can talk about that with you. Any other questions that you want to ask? Anyone?
Was it useful?
Of course, it was amazing. I mean, I'm so excited to see as somebody is working on the same direction that we have been working. Thanks a lot. Although it was a bit long for you to get here, but I'm happy that you could make it and it could host you. It was a very interesting talk. Thank you so much. We can show you a bit of our lab and explain how it is, and then maybe Mehmet can take it for lunch.
Yeah. Maybe one thing also, what we see that there are different kinds of, like in control theory. I have a control theory background as well. Like in control theory, before it was very mechanical, now the digital twins, people think it's a physical sensor data and so on, but now it's more and more abstract. So it's a mixture of physical and so forth. So digital twins are applied also like in control theory, many different abstraction levels. You have seen, we have about, 15 different kinds of digital twins for different purposes. Because and some you send to reviews and they say, where is the sensor data? Still people think very physical. But it's a mixture of these things. So it's basically control. I'm happy that control is now in software technology. Okay, thank you.
Thank you very much.
Thank you.